Hi, I'm AICHEYixiao2020 from Idaho National Lab. My talk today is changing kinetic characterization surface ocean species to understand steady-state performance of oxidative coupling of methane. Methane is a major component of shale gas and can be used as feedstock for high-value chemicals like ethylene, propylene, and benzene. We have abundant domestic shale gas resources. There are different ways to transform methane to ethylene, propylene, and benzene. As indicated, OCM show high productivity in transforming methane to ethylene. This research has been intensively investigated since the 1980s. OCM has a complex chemistry involving the gas phase reaction and the surface reaction. There is no consensus in the active sites and the reaction pathway, and the different active sites have been proposed. OCM still challenged in achieving more than 30% C2 yield, the economic target area. Manganese sodium tungsten oxide is considered as the state-of-the-art catalyst. There's agreement that the CH4 activation on some reactive surface ocean species. However, the nature of ocean species and their role are very much in controversies. There are many works on the OCM catalyst structure characterization by using spectroscopies like XPS, Raman, and EPR. For example, XPS is a very powerful technique to investigate different ocean species by looking at their ocean binding energy. Depending on ocean binding energy, different types of ocean species can be proposed, which are assigned to either selective or non-selective ocean species for the OCM reaction. A lot of reported spectroscopy was done far away from the OCM reaction temperature. Low temperature might not relevant since sodium tungsten oxide melts around 700 degrees C. The spectroscopy information usually contains either the bulk or the near surface information, which might not well present the surface information. Recently, water was proposed to modify the surface ocean species and make it become more selective for the OCM reaction. Overall, the challenge in the catalyst characterization and its complex chemistry of OCM slowed down the OCM progress. In this study, we will going to answer 3 research questions. First, what is the role of catalyst on the catalyst composition in the OCM reaction? Why one catalyst performs better than the other, and how we can approach to a better catalyst design? To address this research question, 3 approaches will be used. Surface reaction will study separately from the gas phase reaction in order to identify the role of the surface reaction and the role of gas phase reaction. Secondly, characterize the surface ocean species and the OCM reaction temperature will be performed. And we're going to build up a relationship between the surface oxygen composition and the OCM performance. In this study, temporal analysis of product will be used to help address the above research questions. And in this study, manganese sodium tungsten oxide-based catalysts will be used. Here, I will give a short introduction on the TAP instrument since it's not a common tool. TAP is a low-pressure pulse technique. Its major components include the pulse valve, microreactor. In the microreactor, a tiny catalyst bed is there, and mass spec, the ultra-high vacuum system. As the movie shows, the gas molecule were injected from the pulse valve and molecule randomly diffused through the reactor, and eventually the gas molecule will be escaped from the reactor and detected by the mass spec. The concept of the TAP reactor is different from the flow reactor. It is a dynamic system. It can reveal more kinetic steps rather than rate-limiting step information from the steady-state flow reactor. Therefore, TAP is a powerful technique to investigate the reaction mechanism and kinetic step. Depending on the number of molecules introduced into the system, gas interaction with the catalyst surface or gas and gas interaction can be studied separately. TAP is a changing kinetic reactor equipped with a fast data acquisition system and high data resolution, which enable the study of short lifetime intermediates. Therefore, TAP is a powerful tool to investigate complex reaction systems like OCM. Let's start from the CH4 activation and C2 coupling. Different amounts of CH4 molecules were introduced into the TAP reactor at 800 degrees C over the state-of-the-art catalyst manganese sodium tungsten oxide. Methane conversion and C2L were investigated. As you can see from the figure in Lucent diffusion region, there is no gas-gas interaction, and we can see that there's no methane conversion in the C2L. When we increase the pore size, gas and gas interaction increase, and we can see the increase in methane conversion and the C2L. When we analyze the transient kinetic information in the Lucent regime, we found out that methane experiences a reversible absorption process. As you can see from the figure, a positive rate is followed by a negative rate. Therefore, CH4 activation is reversible when there is only methane and catalyst surface interaction going on. But methane can be irreversibly activated and converted to products out of the Lucent diffusion region, where the gas interaction becomes significant. Therefore, we can conclude that methane activation is initialized by the surface reaction, and the C2 coupling happens in the gas phase. Then, by composing of CH4 and deuterium, or C2H6 and deuterium, we are able to investigate the activation product of methane and ethane. As you can see the picture on the left, CH3D is the major product of CH4 activation, and C2H5D is the major product of the C2H6 activation. Therefore, we can conclude that CH4 activation is initialized by the catalyst and forming CH3. C2H6 is formed when CH3 radical meet in the gas phase. C2H6 further dehydrogenation initialized by the catalyst and then accelerated by the radical reaction. Furthermore, we can still investigate the type of ocean species for the methane activation. CD4 and 18O2 were co-poses. Different isotope of water was formed. As you can see from the figure, D218O is much higher than the D216O, which indicated that CH4 is activated on some weakly absorbed ocean species site, not the bulk oxygen, lattice oxygen. And the lattice oxygen is less active than the weakly absorbed ocean species. The co-posing of 13CH4 and 18O2 allows us to distinguish the type of oxygen for non-selective products like CO2 and CO. As you can see from the figure, the 13C18O is the predominant product CO, and the 13C16O2 is the major product of CO2. This result highly suggested that lattice oxygen does not play a significant role in CO formation. However, the lattice oxygen influences CO2 formation. The weakly absorbed oxygen species is existed during the gas phase ocean activation process. We apply 16O2, 18O2 pump flow experiment to characterize the type of surface ocean species. The primary process of 16O2 allows 16O2 to absorb on the catalyst and form different types of ocean intermediates. And then a secondary 18O2 process is injected, and the exchange of 18O with 16O intermediates from the primary process can be detected. The formation of 16O2 during the 18O2 process can be ascribed to the existence of some diazo species, and the formation of mixed isotope 16O, 18O can be contributed to the existence of monoso species. As you can see the movie going on here, we observe both 16O2 and mixed isotope during the 18O2 process. However, their kinetic feature is very different and also depending on the catalyst composition. As you can see in the figure that the two 16O2 desorption peak feature was observed, and Mixed isotope desorption is faster than the second peak of 1602. Mixed isotope is more constant in the desorption position regardless of catalyst composition. However, the catalyst composition influences a lot in the 1602 formation kinetics. Furthermore, we studied the steady-state OCM performance at 800 degrees C over different OCM catalyst composition. As we can see from the figure that methane conversion increased by increasing the gas residence time. At the low residence time, ethane is the primary C2 product, and conversion of ethane to ethylene by increasing the gas residence time. C2 selectivity increases when gas phase ocean substantially decreases. And a prediction can be made based on the steady-state performance and the catalyst surface ocean composition. The y-axis information was obtained from the steady-state performance, and then the x-axis information was from the 1602-1802 pump product experiment. The colored bar represents the diazo desorption peak time, and the diameter of the circles here present the 1802 conversion during the 1802 process. And the conversion of 1802 is an indicator of ocean activation efficiency. As we can see from this relation here, we can conclude that higher ratio of diazo to monoso species, the higher selectivity of the OCM performance will be obtained. The higher ratio of diazo to monoso species also lead to higher 1802 conversion, means it's higher in ocean activation efficiency. The optical diazo characteristic desorption time for the optimal OCM selectivity can be estimated between the time of 0.22 and 0.24 seconds. Therefore, diazo species are mainly responsible for the increased C2 selectivity during the OCM. Now, we come to the conclusion. The role of the catalyst composition is going to activating the gas phase ocean to the weakly absorbed ocean species. The weakly absorbed ocean species activate the methane in forming CH3 CH3 radicals coupling in the gas phase. CO was formed mainly via the oxygen with the CH3 radical. CO2 formed mainly via the surface process. C2H6 further dehydrogenation to C2H4. The bulk or lattice oxygen is mostly inert compared to the weakly absorbed ocean species in the methane activation. Differentiation of monosos and diazo species and optimal surface residence time correlated to the mechanism loading is important to explain why one catalyst performs better than the other one. And then diazo species that are mainly responsible for the increased C2 selectivity during the OCM. Transient kinetic method can uniquely apply studying the principle of OCM reaction and the catalyst characterization. It tells how and why information a complex industrial material perform better than the other one at the reaction temperature. The end, I want to acknowledge our funding agency and our transient kinetic group in Idaho Falls.